In this video, we continue our study of ideals with a discussion of the ideal of a variety. First, we're going to start by reviewing the definition of an affine variety, the definition of an ideal, and then we'll look at a particular example of an ideal. That's the ideal generated by the polynomial functions f sub 1 through f sub s. And then after we review all of that, we're going to talk about a new type of ideal called the ideal of V. It's denoted by I of V, and we're going to prove that it actually satisfies the requirements of an ideal. And then we'll look at a couple of examples. So first, let's look at the definition of an affine variety. Affine varieties are typically denoted this way. We have V of f sub 1 through f sub s, and this is the set of points in n-dimensional affine space, that's what this says, such that all of those polynomials are zero for I equals 1 through I equals s. Or in other words, if I take f sub 1 and set it equal to 0, f sub 2 and equal to 0, and all the way down through f sub s and set that equal to 0, I've got a system of s polynomial equations and n unknowns. And those n unknowns are x sub 1 through x sub n when our polynomials are in this polynomial ring with coefficients in the field k in the variables x sub 1 through x sub n. This affine variety is the solution set of this system of s polynomial equations and n unknowns. It's just a set of points in n-dimensional affine space, and that set of points may be finite, might have just a list of points that we can write down, or that set of points may be a curve or a surface or a hypersurface. All of those are affine varieties. Now I want you to notice that I did something a little different at the beginning of this video. Rather than listing this ordered n-tuple, and a sub 1 through a sub n as an element of n-dimensional affine space, from now on, I'm just going to use a to represent a generic point in n-dimensional affine space. That way I can save a little bit of time and I can write this instead, but remember this is actually an ordered n-tuple. Okay, so that is the first object, one of the most important objects in algebraic geometry. Another important object, a very important mathematical object that we talked about in the last video, is an ideal. Now, an ideal is a subset of this polynomial ring, so it's a set of polynomials. That satisfies these three conditions. So the zero polynomial has to be a member of that set. And if we have two polynomials in the set, their sum has to be in the set. And then if we have a polynomial in the set, and then we have any old polynomial in our polynomial ring, we can multiply those together and we're still going to have a polynomial in the set. Now, initially that seems very abstract, and I suppose it is. But when you think about this system of equations, it has a very intuitive interpretation, and this is a very meaningful object. So let's look at a particular ideal. We talked about this in the last video. This is called the ideal generated by the polynomial functions f sub 1 through f sub s. Now, that is denoted this way. And this is the set of all polynomial functions that can be written in this form. It's the sum as I goes from 1 through s of h sub I times f sub I, or if you prefer, you can expand it. That's h1 f1 plus h2 f2 plus h3 f3 all the way through h sub s, f sub s, where the h sub I are just polynomial functions in that ring. So they're any old polynomial. Now, in the last video, I proved that this is an ideal. Let's think about what this means. So I have this set of polynomials over here that define this ideal. And the ideal generated by those functions comes from taking all of those functions, multiplying them by polynomial functions from our polynomial ring, and then adding them together. Well, this is meaningful and closely related to this system of equations because this is what it says. If f sub 1 through f sub s defined some system of equations like this, if I take each of those equations and I multiply them by a polynomial function in our polynomial ring, I get h1 f1 equals 0 plus h2 f2 equals 0 plus h sub s f sub s equals 0. And we have all of those. If we take all of those that are equal to 0 and we add them together, what we get is a polynomial consequence of the fact that these polynomials are all equal to 0. We get another polynomial that must be 0 because these polynomials are 0. So the ideal generated by f sub 1 through f sub s is a set of polynomials, or the set of all polynomials, in that polynomial ring with coefficients in the field k that must be 0 when the original defining functions, the generating functions of that ideal, are equal to 0. So the textbook authors call this a set of polynomial consequences of these functions f sub 1 through f sub s. The way I want you to think of it is that it's a set of polynomial functions. So keep that in mind. But these functions all have to be 0 if the original functions are equal to 0. So this is powerful. Here we're saying that these particular functions have to be 0. Here we're talking about a set of functions that must be 0 if all of these are 0. This is a much richer class of functions, and it turns out that it's an ideal. These three conditions are satisfied by the ideal generated by f sub 1 through f sub s. So now you can see that these ideals and the affine varieties that we started with are intimately connected, because when I'm talking about an ideal generated by f sub 1 through f sub s, I'm taking the polynomial functions, or the polynomial equations, excuse me, that define our affine variety. And then I'm multiplying them by generic polynomials, and I'm adding them together, and I'm saying those polynomials are 0 too. So remember, affine varieties are solution sets of the system of equations. They are points in n-dimensional affine space, which may be just a finite number of points, or points along a curve, or points along a surface, or points along a hypersurface, whereas ideals are polynomial functions that satisfy these conditions. But more importantly, if you're thinking of an ideal generated by polynomials f sub 1 through f sub s, this is the set of all polynomials that have to be 0 when the original system of polynomial equations is satisfied. So let me write that down as well. It's the set of all polynomials that must be 0 when this is equal to 0, or in other words, that's when the original system of equations defined by f sub 1 through f sub s is satisfied. At the end of the last video, we talked about this very important fact, and we looked at a couple of concrete examples. We said that affine varieties are not determined by polynomials. Instead, they're determined by ideals generated by polynomials. So one of the things that we looked at in the last video was the fact that you could have two different sets of polynomials, f sub 1 through f sub s. You could say that those are the basis functions for that ideal. If you have two ideals that are the same and they have two different sets of basis functions, they're going to correspond to the same affine variety. So basically, you can take that system of equations and manipulate it. You can come up with any other system of equations you want, as long as that system of equations is sort of equivalent in the sense that the ideals generated by the new system of equations, or the ideal generated by the new system of equations, is equal to the ideal generated by the old system of equations. Well, the solution set is going to be exactly the same. And the solution set is our definition of the affine variety. And I think that's consistent with your intuition, maybe not in abstract, but when we looked at those concrete examples at the end of the last video, hopefully that sunk in as you see the examples from pre-calculus, where you take that system of equations, you write it as a different system of equations, and you see that the solution of the new system is the same as the solution of the old system. And those are the algorithms that we tend to follow when we're solving either systems of linear equations or systems of nonlinear equations in a pre-calculus class. So this is abstract, but we have many concrete examples from our previous experience. So now we have another ideal that we'd like to discuss. This is called the ideal of a variety. So let's say you have an affine variety. So this affine variety is defined in terms of some polynomial functions f sub 1 through f sub s, and we've got a solution set of that system of polynomial equations in n-dimensional affine space. Then we're going to define I of v to be the ideal of the variety. What this is the set of all functions f, all polynomial functions f in our polynomial ring and n variables, such that that polynomial is 0 for all points in the affine variety v. If you're saying, what? Let's examine this a little bit further. It's easier if we look at a concrete example. So let's look at a concrete example. Remember we talked about the twisted cubic? Turned out to be a curve in three-dimensional space. It was defined by the functions y minus x squared and z minus x cubed. So this is the set of all points in three-dimensional space such that this polynomial is 0 and this polynomial is 0. If I add the x squared to both sides, I get that. And if I add the x cubed to both sides, after I set that equal to 0, I get that. And it turned out that this gave us a curve, and we came up with those parametric equations for the curve. If x equals t, and y equals t squared, and z equals t cubed, where t is some real number, then these ordered triples are the solutions, or are the set of points that belong to this affine variety. And we were able to graph these in CalcPlot 3D and actually look at this and why it might be called a twisted cubic. We've got this cubic surface that when you look at the cubic surface intersecting with this parabolic surface, they intersect in a cubic way, but it seems to be twisted, and it's twisted by the fact that we're looking at the intersection with this parabolic cylinder. um, so that is an example of a variety. The ideal of that variety, where the variety is defined by these two polynomial functions, is the set of all polynomial functions in the variables x sub 1, or excuse me, in the variables x, y, and z, where the coefficients are in the field of real numbers, such that f of a is equal to 0 for all a in the variety v. So these are all of the other polynomials that are equal to 0 when we're on that twisted cubic function. Now you've probably, or many of you may have heard this terminology before, but some of you haven't, or perhaps haven't. So I'll define this for you. We say that a polynomial vanishes at a point if it's equal to 0 at that point. Or we say that a function vanishes at that point if evaluating the function at that point gives you 0. So this ideal of the variety is the set of all polynomials that vanish on the points of that twisted cubic for this particular example. Now, since we know the parameterization of the twisted cubic, since we know that this can be represented as a set of ordered triples with coordinates t, t squared, and t cubed, it's pretty easy to find some polynomials that would belong to this particular affine variety. So because we know that the variety is equal to this, is a set curve in three-dimensional space, we can see that, let's say, x times y minus z is given by t times t squared minus t cubed. That would equal 0 for all points on V, because if we have an ordered triple with coordinates given by these parametric equations, x times y minus z will equal 0 the whole time. Another polynomial function that would equal 0 is y squared minus x times z. That is equal to 0 when, or that is equal to 0 when x is equal to t, y is equal to t squared, and z is equal to t cubed, because if I take y squared, or if I take y and I square it, that's t squared squared, and then I subtract t times t cubed, well, that's t to the fourth minus t to the fourth, so that's 0. That's going to be 0 on V for every point that has this form, or that's 0 for every point that has this form, so therefore this polynomial is 0 on V. And since these polynomials are both equal to 0 for all points in this affine variety V, these polynomials are functions in this set. They're polynomials in this polynomial ring with coefficients in the reals that are polynomials in the variables x, y, and z that are equal to 0 for all points on the affine variety. So this polynomial belongs to the ideal of the variety, where this variety is the variety that we know to be, or that we call the twisted cubic. And this polynomial belongs to the ideal of the variety. So this is a set of polynomials that vanish or are all equal to 0 when we're on this set of points in n-dimensional affine space. So the ideal of the variety answers this question. Or the ideal of a variety answers this question. If we're given a variety, in n-dimensional affine space, we already know that f(1) is equal to 0 and f(2) is equal to 0. All of these guys, f sub s is equal to 0. So we know that those polynomials are 0 on the affine variety because that's the definition of the affine variety. This is a set of points where these s polynomial functions are all equal to 0. Typically, we write it like this: f(1) equals 0, f(2) equals 0, f sub s equals 0. Those are all going to be 0 for every point in V. Now, that's not the question. The question is, are there other polynomials that vanish on V? Sorry about that. There. And if so, can we find them all? So with that question in mind, when we talk about the ideal of a variety, what we're talking about is this. This is the set of all polynomial functions in our polynomial ring such that those polynomials are equal to 0 or they vanish at all points in the variety. Now, we just labeled it the ideal of a variety. We haven't yet proven that it's an ideal, so let's prove that it's an ideal. This is lemma number 6 in the book. It just says that this is an ideal. So let's prove it. Now, first of all, if we're proving that a set is an ideal, we just need to show that those 3 conditions that we talked about are satisfied. So 0 has to be a member of the set. If 2 polynomials are in the set, their sum has to be in the set. And if we're talking about a polynomial that's in the polynomial ring and we multiply that by a polynomial in the set, when you multiply them together, you're supposed to get a polynomial in the set. If all of those are satisfied, then you're talking about an ideal in a polynomial ring. So the first condition is actually really easy to check. So let's say that we're talking about the 0 polynomial. Remember what the 0 polynomial is. That is a polynomial f defined in this way. It's the sum over alpha of 0 times x to the alpha. It's equal to 0 because all of the coefficients are equal to 0. Obviously, it does not matter what you plug in for a here. no matter what x is, and when I take x and I raise it to the alpha power, and when I actually work that out and then I multiply them all by 0, I'm going to get 0. So if we're talking about the zero polynomial, obviously the zero polynomial is 0 for all points in the affine variety V. So that means this polynomial must belong to the ideal of the variety, I of V. Now we'd like to prove the second and third requirements. So let's let F and G be members of the ideal of the variety, or this I of V that we're proving is an ideal. And then let's let H be just some generic polynomial in our polynomial ring. Well, if F and G belong to this set, then obviously f of A equals 0 and G of A equals 0 for all A and B. So if we evaluate F plus G at A, by definition, that's F of A plus G of A. And since F and G are in this set, this is 0 and this is 0. So we get 0, and that's going to be true for all A in the variety V. So that means that F plus G is in the ideal of the variety. Now if I take F and I multiply it by some other polynomial H, if I evaluate that at a point A in the affine variety V, I get H of A times F of A. Now H of A may not be 0, but F of A is equal to 0 because F belongs to I of V, so we end up with H of A times 0, which is of course 0. So this is equal to 0 for all A in the variety. So H times F is in the ideal of the variety. So clearly this is an ideal. If we have, or it contains the zero polynomial, any two polynomials in this set, or if we have any two polynomials in this set, their sum is in the set. And if we take any polynomial in the set and we multiply it by another polynomial that's not in the set, we're still going to get 0. We're still going to be in the set. So this is an ideal. Now let's look at two examples of ideals of varieties. Our first example is pretty simple. Let's say we're talking about the variety given by all of n-dimensional affine space. In that case, the ideal of the variety is the set of all polynomials in our polynomial ring such that f of A equals 0 for all A in the variety. Well, if that variety is all of n-dimensional affine space, we're talking about the set of polynomials that are equal to 0 at all points in n-dimensional affine space. Now, remember what we talked about earlier, had this proposition we called proposition 5. It said that if K is an infinite field, then the following are equivalent. Then F is equal to the 0 polynomial in our polynomial ring if and only if F as a function, that mapping from n-dimensional affine space to K, is the 0 function. So these are equivalent to each other. Now remember, the 0 polynomial is the polynomial whose coefficients are 0. This is saying that no matter what point we pick in n-dimensional space, we always get 0 out from this. these are equivalent to each other. They're interchangeable. This is equivalent to this, or this implies this, and this implies this, if K is an infinite field. So this ideal of the variety, which is the set of all functions that are equal to 0 at all points in n-dimensional affine space. Well, it turns out if we're in affine space for a field K and that K is an infinite field, this is saying, well, I'm looking for the ideal of V is the set of all functions that are equal to 0 for all of n-dimensional affine space. Well, if all of those functions are equal to 0 for every point in n-dimensional affine space, then we're guaranteed that that function is the zero polynomial, provided that K is infinite. So Proposition 5 was written this way. Another way to state Proposition 5, now that we know what an ideal of a variety is to just say that the ideal of the variety is the zero polynomial when K is infinite, or an infinite field. Let me specify that it's a field. We know from context that it's a field. And when we see a 0 like that, we're referring to the zero polynomial. So that's a good fact to make note of. We should be aware of the only polynomial that is equal to 0 at all points in n-dimensional affine space is the zero polynomial. Oops. This is where the field is all of n-dimensional affine space, so we should write it like that. The ideal of n-dimensional affine space is the zero polynomial. Okay, that's our first example. Now there's another example, and again, it's related to that twisted cubic. We've got our twisted cubic, set of all points in three-dimensional space such that y is equal to x squared and z is equal to x cubed. Now we've already shown that the twisted cubic can be parameterized in this way, excuse me, where t is a real number. Now here's the claim. The claim is that the ideal of the variety given by that twisted cubic turns out to be the ideal generated by the polynomial functions y minus x squared and z minus x cubed. Now, I don't remember if well, actually, I do remember that I talked about what this is. Just as a reminder, remember this is the set of all polynomials that can be written in this way. It's h1 times y minus x squared plus h2 times z minus x cubed, where h1 and h2 are in the polynomial ring. And the claim is that those are equal to each other. In order to prove that two sets are equal, usually what we do is we show that every element of this set is in this set. So we show that this one is a subset of this set. And then we go the other way. We show that all of the elements in this set belong to this set. So if this set is a subset of this set, and this set is a subset of this set, the sets must be equal to each other. So we'll prove this direction first. First, we'll show that every polynomial in the ideal generated by these two polynomial functions belongs to the ideal of V. And then we'll go the other way. Okay, since we know that these two functions are equal to 0 on V, If we let F be a member of this set, then F of A is going to be given by h sub 1 of A times this polynomial y minus x squared evaluated at A. And I'll just write it like that. Plus a second polynomial h sub 2 of A times the second polynomial z minus x cubed evaluated at A. I'll write it like that. Well, since y minus x squared is equal to 0 at every point in this affine variety, and z minus x cubed is equal to 0 at every point in the affine variety, this is equal to 0 and this is equal to 0. So f of A must be 0 for all points in the affine variety. And if f of A is equal to 0 at all points in the affine variety, well, where's our definition? Well, then that's the definition of being an element of the ideal of the variety. Since being in this set means that we're in this set, we've just shown that this set is a subset of this set. All of the functions in this set belong to this set. And the second part where you're showing that all of the elements in this set belong to this set is a little bit harder. It's actually not too bad, but in order to do that, we're going to have to take sort of a detour. And I'm just going to call that I of V, but remember we're talking about the variety given by that twisted cubic. In order to show that I of V is a subset of this set, first we need to show that any polynomial in our polynomial ring can be written as h1 times this first function plus h2 times the second function plus a remainder r, where that r can depend on x only. And the reason we're proving that is because that once we know that fact, it'll be useful in showing that this inclusion is true, that all the elements of this set belong to that set. So we're in the polynomial ring with coefficients in the field of real numbers in the variables x, y, and z. And we want to show that every polynomial can be written in this way. And we're going to say where r is a function of x only. So it does not depend explicitly on y or z. In order to prove that every polynomial in our polynomial ring can be written that way, let's talk about a monomial. So let's let f just be, as a special case, x to the alpha times y to the beta times z to the gamma. So it's just a monomial. Well, if I want to write this in this form, I can algebraically manipulate this expression so that it includes a y minus x squared as part of it and a z minus x cubed as part of it. And if you're saying as part of it, what do you mean? These are going to be factors in various terms of this polynomial after doing some expanding. You're saying, how can you expand a monomial? Just watch. I've got x to the alpha over here, And I'd really like this to be written in terms of y minus x squared. So I can make that happen. I can put a y minus x squared over here as long as I compensate. If I'm subtracting x squared from y, I can compensate for that by adding x squared to this expression. So x squared plus y minus x squared is just y. So that's all y. And we want all of that raised to the beta power. Similarly, if you have z to the alpha or z to the gamma, and you want this to be, or you want to be able to expand this in a certain way so that it has factors, has various terms involving factors of z minus x cubed, you can make that happen as long as you add x cubed to that. So if we take x cubed and we add z minus x cubed, the x cubed is reduced and you just have z. So this is a z to the gamma power. Now, if you look at this, I know it looks like a trinomial, but if you think of it the way that you would think of a binomial, you think of this as the first term and this is the first term, or this is the first term and this is the first term, and you raise this expression to the beta power. The first thing that you're going to get is x squared to the beta, and then you'll have a constant times x squared to the beta minus 1 times one of these, and then a constant times x squared to the beta minus 2 times two of those. And you're just going to go down the list with our binomial expansion. So if we were to actually sort of FOIL this out, if we were to write this beta times and then distribute, the first term would be an x to the 2 beta. It'd be x squared to the beta, which simplifies to x to the 2 beta. And then every other term would involve x squared to the beta minus 1, x squared to the beta minus 2, x squared to the beta minus 3, and so on until you get to x squared to the first and x squared to the 0 times powers of y minus x squared. First raised to the first, and then raised to the second, and raised to the third until you get to the y squared minus, or y minus x squared to the beta. So what we end up with when we expand this is x to the 2 beta plus terms involving y minus x squared. And similarly, if you take this and you expand it, you're going to end up with an x cubed to the gamma. So that's x to the 3 gamma. And then the next term would be a constant times x cubed to the gamma minus 1 times z minus x cubed. And then the next term after that would be a constant times x cubed to the gamma minus 2 times z minus x cubed quantity squared. And so every other term except for that first term is going to have factors of z minus x cubed in it. So what we'll have here is x to the 3 gamma plus terms involving z minus x cubed. So if I write all of this out, if I expand this, if I take the leading terms and I multiply them together, I've got x to the alpha times x to the 2 beta times x to the 3 gamma. And we know we can add the exponents. So we have that plus a whole bunch of terms involving this times x to the alpha, plus a whole bunch of terms. Well, we're going to have this times all of those, and then we're going to take that times all of those, and we're going to distribute to all of these guys over here. So what we will end up with if we did that expansion is some function of x and y times y minus x squared plus some function of x and y times z minus x cubed. So this is, well, we've got this just x to some power plus this, and this is where f is actually just a generic monomial that started as x to the alpha, y to the beta, and z to the gamma. Now, that was just for the monomial. And the claim was that every f in this polynomial ring with coefficients in the field R in variables x, y, and z can be written this way. Well, we know that every polynomial is just a linear combination of monomials. Since every monomial can be written in this way, when we take these monomials and we multiply them by constants and add them together, the resulting f can be written this way as well. So we'll say since an arbitrary f in our polynomial ring is a linear combination in R. So we're taking real numbers and then we're multiplying them by these monomials. I wrote little, linear combination in R of monomials. Then every f can be written in this form. So f can be written as h1 times y minus x squared plus h2 times z minus x cubed plus r, where r is a function of x, where h1 and h2 are polynomials in our polynomial ring. And the polynomial ring we're interested in is this one. So now we're ready to prove the other inclusion. We want to show that if a polynomial is a member of the ideal of the variety, then that polynomial has to belong to the ideal generated by the polynomials y minus x squared and z minus x cubed. And we can do that given that every function f can be written in this way. So let's just start by assuming that we have a function in the ideal of the variety. Now remember what the ideal of the variety is. This is the set of all functions in our polynomial ring. This is the particular polynomial ring we're interested in, such that f of a is equal to 0 for all a in the variety v. And the variety v was defined by y minus x squared and z minus x cubed. Well, since f is in the ideal of the variety, or since it's in I of v, we know that it belongs to our polynomial ring. Since it belongs to our polynomial ring, we know that it can be written this way. And this is where h1 and h2 are polynomials in our polynomial ring. Well, since this belongs to this, or since this belongs to this set and it can be written this way, and f of a is equal to 0, then that means this function evaluated at any point a in our affine variety is equal to 0. So that would be f of a is h1 of a times this polynomial evaluated at a plus h2 of a times this polynomial evaluated at a, plus r evaluated at a. Now, since a belongs to this variety, we know that this is 0 and this is 0. So all we end up with is that f of a has to equal r of a, and r of a and f of a is also equal to 0. So we must have r of a equals 0. But remember, r can be written as a function of x alone. If a is in this affine variety, since we know a parameterization of that affine variety, a can be written this way. So a is the ordered triple given by t, t squared, and t cubed, where t is a real number. So r of a is actually equal to r of t because r does not depend explicitly on x or y or x. And this is r of t now, and doesn't explicitly depend on y or z. I said the wrong variables. R depends only on x. So since r depends only on x, r of a is the same as r of t, and we're saying that this is equal to 0, where t is any real number. Because if t is any real number, then this point lies on the variety. Well, we know that if r of t is equal to 0 and this t is coming from this field r, which is an infinite field, well then r of t has to be the zero polynomial because of proposition 5. Remember, the zero proposition 5 said that if we have a function, or if we have a function that is equal to 0 for all points, or if we have a polynomial function that's equal to 0 for all points in some infinite field, well then that polynomial function must be the zero polynomial, because that field is infinite, and vice versa. It goes both ways. So this is r of t is equal to 0, the zero polynomial in r of x. Of course, if you wanted, you could write that as r of x rather than r of t. So if r is equal to the zero polynomial, well then we have f must be equal to this. Well, and that's the definition of belonging to the ideal generated by the polynomial functions y minus x squared and z minus x cubed. Okay, so what have we shown? We have shown that if f belongs to the ideal of the variety, because every polynomial in this ring can be written in this way, and that field is an infinite field. We say the only way that you can belong to this set and have this equal to 0 is if r is the zero polynomial, and if r is the zero polynomial, that means f belongs to, or looks like this. And if f looks like this, it belongs to this set. So we have just shown that if f is an element of the I of v, then f has to be an element of this. So we've shown that this set is a subset of this set. Earlier, we showed that this was a subset of this set. Now we've shown that this is a subset of this set. So that means that they're equal to each other. So the ideal of the variety happens to be the ideal generated by the polynomial functions that define that variety. So we'll say In this case, the ideal of the variety generated by these functions is equal to the ideal generated by the functions. An interesting question is that always the case? And the answer to that question is no. There is one set inclusion. One of these sets belongs in the other set, but it doesn't necessarily always go both ways. They're not necessarily equal to each other all the time. They happen to be equal in this case. But in general, one of these sets tends to be larger than the other set. And we'll talk about that in the next video. So let's just briefly recap what we've studied so far. We have affine varieties. Those are a solution set of systems of polynomial equations. And then we have ideals, which are sets of polynomials. And these are linked to each other through just as one specific example, the ideal generated by the polynomial functions that define the original affine variety. So the ideal generated by this set of polynomial functions is a set of polynomials that you get when you take these polynomials, you multiply them by other polynomials, and then you add them together. Now, this is related to this in the following way. This set of polynomials is a set of all polynomials, and that's a pretty strong word. It's all polynomials in our polynomial ring that must be zero when the system of equations is satisfied. So it's not just that these S polynomials are zero. These are all the polynomials that have to be zero when these guys are zero. And we talked about in video 1.4.1 that affine varieties are not determined by these S polynomials. They're determined by the ideals generated by the polynomials. So these polynomials may not be the basis for the ideal. There might be a different basis for the ideal. And that allows us to take a system of equations and manipulate it and then solve the resulting system of equations instead and be able to end up with the same solution set. And again, the solution set is the affine variety. So we reviewed all of that, and then we talked about the ideal of a variety, and that's right here. The ideal of a variety is just the set of polynomials such that those polynomials, it's a set of all polynomials that vanish when we're on the variety. And remember what vanish means. We're just saying that a function vanishes at A if you evaluate it at A and you get zero. So we're answering this question. We're saying if we do have an affine variety, that's a set of points in n-dimensional affine space. We know that certain polynomials are equal to zero. The question is, are there other polynomials that are equal to zero or that vanish as well? And can we find them? The set of all polynomials that equal to zero in or on that set of points V is called the ideal of V. And we proved that this was an ideal. And then we looked at a special example. If our variety happened to be all of n-dimensional affine space, we showed that the ideal of n-dimensional affine space is just the zero polynomial, as long as we're dealing with an infinite field K. That's just a result of proposition 5. And then we looked at an example involving the twisted cubic. And we showed that the ideal of the variety given by the twisted cubic is the variety. I'm sorry, excuse me. We showed that that is the same as the ideal generated by those two polynomial functions, which led to a pretty interesting question. The question is the ideal of the variety generated by the functions f sub 1 through f sub s, or defined by the functions f sub 1 through f sub s, is it always equal to the ideal generated by the polynomial functions themselves? And we'll say not always. That was the answer to that question, and we'll talk more about that question next time.